Welcome back, and thanks for following these set of videos on the 8086. In the last part, I added 3 test lines of move AL20, move AH60, add AL12. I obtained the machine code for those assembler instructions and split the machine code into separate bytes, created 2 binary files, and uploaded those into the 2 EPROMs, and then stepped through the code using an Arduino to display the data lines. And we could see those appearing on the data lines as read from the EPROMs and has been read in by the 8086. Before I move on to the next stage, I want to expand on the 8086 operation and memory segmentation. We know the 8086 has 20 address lines in total, and this allows the 8086 to address 1 meg. But internally, it only uses 16-bit registers and a data line of 16 bits. This 16-bit means it can only actually operate with 64K at a time, as 16 address lines can only address 64K. So it uses the first 4 of the 20-bit address to set segments or blocks of 64K. So the first 4 address lines point to the 64K block it's currently working with. The 8086 as segment registered refers to as CS or code, SS or stack, DS is data, ES is extra, which we see here in the 8086 datasheet. I'm not going to go into this further because it starts to get very technical rapidly. But when we were coding the AT system at Marconi, which started me on this path of videos, there was a huge amount of code which divided the code into code, data, and stack, which was used for accessing our onboard RAM. In this series, I'm just running a short bit of code to write to an LCD display, so I'm only ever working with 64K in total. So I don't really need to get into the complexity of these stacks, or jumping outside by 64K. Here on the same page, the datasheet mentions that I have the fact that on reset, the 8086 starts at address FFFF0, so 5 bytes. I'm only using 64K, so I'm effectively ignoring that first byte. I'm only interested in the last 4, which make up the 16 bits. I have no choice but accept the FFFF0 location, as that's where the 8086 starts. You saw to add the 2 EPROMs, I had to drop off the A0 connection and use the A15 address. This A15 address comes from the last bit from the first 4 bits of the 20 address lines. But as I'm only using 16 bits and so restricted to 64K, that's why I just connected this bit on the EPROM to +5 or 1. So for the EPROM, this top address bit of the 16 address will always be 1. I can do this only because I'm only ever using a 64K block for this coding exercise. So in this 64K block, it runs from 000 to FFFF. I've configured the memory EPROM to start at this address 8000 and use the NAND gate to enable the EPROM only with that address 8000 to FFFF. Any addresses outside that range, like say 6000, will therefore not relate to anything in the EPROM. Now here, the 8086 starts at FFF0, which is why I set the test lines to start at FFF0. But as you can see, the code increments sequentially from 2 to 4, then 6, and obviously it's going to go through 8A, C, and E, and then there's no address after that. So I have to write a jump statement. This jump statement will allow me to jump further up into this memory block to give more space to write code, and that's what I'm going to do in this video, write a jump statement. There are different types of jump statement. There's a jump near and short, where jump near is plus or minus 128. And jump short, you're only going to need 2 bytes because when you're using 2 bytes, it's greater than the 128. So I'm going to jump back 2057. So that's minus 2057. So I need to write the instruction to jump minus 2057, which in hex is 809, obviously minus 809. So minus 809 is 2's complement, which is F7F7. 2's complement is a way of showing binary numbers in positive and negative. You can look up 2's complement and see how to work that out and how minus 809 hex relates to F7F7. But I'm not going to really go into this, but just take it from me that the jump back for 2057 is going to be F7F7. So the instruction for jump is E9. So it's going to be E9 F7F7. Obviously, I need to place this jump at FFF0. So when the 8086 restarts, it jumps to FFF0. It reads this instruction E9 F7F7, which says to it jump back 2057. So it jumps back. And when it jumps back by 2057, the address is F7EA, which is doesnt binary. The code I'm going to place then at this address, we're going to start. We can then write more code because obviously we've got more space to write here than we would have if we were trying to write something in here. And that's the whole reason why we're jumping back to 10, try and write. We can jump back to any location. We could jump back all the way up to 8,000 or 9,000 or anywhere within that memory location that we have the EPROM defined as. I'm going to then write some bits of code in there of move AL26, add AL2, and then I'm going to use this out statement. So we can actually write the value of AL out to a port. So the out statement is an assembler instruction within the 8086 to write to a port. I'm just defining the port 0 at the moment, and the instruction for out is E6. And then I'm going to have another jump, which is going to say jump back to the start. So this jump start will actually, in machine code, is going to be EBFA. So EB is this jump start, which is this jump near. Whereas you'll see the other jump is E9, which is the jump short. So we're going to test both jumps. We're going to jump back, then go through these instructions, then jump up to the start, and go through these instructions, back, jump up to the start, go through these instructions, jump up to the start. So we're going to see two jumps, jump, run, and then we'll have a little one just circling around there, just to show that the processor is actually reading, it is understanding the commands of jump, and we are able to jump back, and then we can move on from there. The jump near, as I said, is EBFA, so it's a single byte. So this one here, this jump start. So when we jump back, we're going to jump back that distance 2057, which will take us to address. So FFF0 minus 2057 is F7EA. So, but what does the EPROM see? Because F7EA is here, that's the F, that's the 7 obviously, the E, and then the A, which is 10. But that's the address, but that's not what the EPROM is going to see. You remember we said we're dropping off this A0. So the EPROM does not see this address. It doesn't see this last one, but it sees the one that we've added on here. So we're going to have to put a 1 in here and move all of these across to the right. So it's going to look like that. So we drop off the 0 because the A0 is not connected to the EPROM. We then move everything across to the right, adding the 1 at the front there. So you're going to get that 0 move across to there, that 1 move across to there, and that 1 move across onto there, which gives us this. So you'll see it's all moved across. That 0's gone onto there, moved across. And what is that address? FFF5. So that's where we're actually going to write our code within the EPROM, because the EPROM sees this address, F7EA, with the A0 dropped off as FFF5. So these are the codes that we have that we're going to put in as the move AL, which is the B01A, the 0402, the E6, etc. So in this side, this is going to be the low bytes and these are going to be the high bytes. So that's how we're going to split the code up into the high bytes and then the other lot going into low bytes. And for this jump at the bottom here, which we're going to put in the location FFF0, the E9 F7F7, it's going to look like this. Again, with it split into the two EPROMs, with these bits being in one EPROM and these bits being in the other EPROM. So these will be in the lines D0 to D7, and these pieces here will be in the other EPROM that's got the D8 to D15. So now we need to code this information into the EPROM. So we go back to our binary files, we have the create file, and this one I'll just change the text on this to create odd. So we have in behind here the code. This one creates the file for the D0 to D7 that we built before with just the test files in here. And then here we have the ones from D8 to D15, and we had the test bytes in here. We need to change this. So if we go back to the code, we just can pick that code up and then remove this code here and put the other bits in. So let's see if we go back. But I just want to check this jump. As we've seen, we're doing we've got two jumps, a jump near and a jump short. And the jump near just does the short jump. So this short jump here, what we're doing is we're running this little move into AL, this add AL, and then this out statement, and then we're jumping back. So we should be seeing then on our program, if we start this running round. So this jump start here is using the EB because it's the jump near, and the FA should jump it back. What we want to jump back is to the start, so to here. So that's 1 byte, 2 bytes, 3 bytes, 4 bytes, 5 bytes, 6 bytes. So we need to jump back 6 bytes. So if we were pointers here, effectively we're saying to the instruction pointer, jump back 6 bytes and reset the instruction pointer to point back to here. So I'm just going to check if that FA is right. So if we have 6 bytes, so 6 in hex is 0, 0, 0, and then 0, 1, 1, 0. And for negative numbers, what's happening is this first bit is being set to 1 to indicate it's negative. So when we call that instruction, it knows it's negative. It's got a thing called 2's complement. So the first thing we do is we add 1 to this. So it's 0, 0, 0, and then we do 0, 1, 1, and then 1 because we've added 1 to that. And then what we do is we just simply invert those numbers. So effectively we go, the 0 goes to a 1, the 0 goes to 1, the 0 goes to 1, the 0 goes to 1, 0 goes to 1, and then the 3 ones there go to 0. And that's F and 8. So actually, where I've put in here, it's FA. That's not actually correct. That's F8. So although I've said there FA, and that's actually F8, and that should be F8 because we're only jumping back the 6 bytes. So here, if that instruction was at say FFF0, whatever, we would then jump back 1 to jump it back to the start here. So that should be 6 bytes moving back. So now if we go back onto our Visual Studio, and then we'll enter the code into here, and using our new address, we know that the EPROM address, so that when we jump back to F7EA, F7EA isn't what's seen by the EPROM. As I say, we need to drop off this 0 because we're not using the A0. So actually the EPROM sees it as FFF5. So next we'll just move on to coding that into our binary files. So now we move on to coding the 2 binary files. So if we open our Visual Studio, we have the 2 forms. I've tidied that up a little bit with the buttons. I've put a create out file and create odd. So if we go to the first one, which is, we need to change this code here. The 86 starts at FF0, but obviously with the drop off of the A0, the EPROM sees it as FFF8. So we need to code our jump into here. If we go back, what we need to code here is the E9 F7 F7. So as this is the D0 to D7, we need to put E9 and F7. And again, if we do the same on here, we don't need this last one because we've only got the 3 commands. So if we go back, we're coding here F700. And then we need to add somewhere the other values. So here we do. And if I just copy the similar line like that, and we're going to have here, if we go back, we need to start at FFF5. So that's FFF5. And then it'll be 6, it'll be 7, 8, 9, and A. And we need to code B004E6. B004E6. And then EB. So in fact, we don't need those last two addresses. Okay, need those. And the code from the other side is 1A0200. 1A0200 F8. Okay, so that's it coded. So now if we run this, create that file, create the odd file. So that's 2 files created. We can have a look at that by using PowerShell. There's our 2 files we just created. If we do format -hex ROM 8086.bin. This should output that file. So it's dumping the entire file, and here we can see at the bottom where we put in our location FFF8 here, the E9 and F7 in our ROM file, and if we scroll up we can see the other bit of code just sitting in here in the FB location, and so we can use that format hex just to have a look at that file. So all we need to do now is use my EPROM programmer and load those two files into the two EPROMs, put the EPROMs in and run the actual code. I'm not going to bother with showing you the film of me taking the EPROMs out and putting the EPROMs in the EPROM program. You've seen that before, but that's all that's needed to do. So what we should be then seeing is when we start it, we should see it jump. So what I'm going to do is connect the Arduino to the address outputs of the latches, and then run that piece of code. And if it's working, we should see the first jump. So we should see the address change from the FFF0 then to the F7EA, and then it should then increment through the code. And then we should see this jump. So we should see the address and jump back. And we should also see the address change here because we're changing the address to 00. So we should see a 0 coming in the output. So that's what I'll do in the next stage. So now I have the Arduino connected to the 16 address pins. We'll just connect to the Arduino and upload the address. And once that's done uploading, we then run the power on to the board and do the reset and run through. Start the serial monitor with power on, stepping through, reset, and what we're looking for is incrementing through the addresses 2 at a time, then jumping to the new address and outputting 0, and then jumping back and incrementing again in a sort of cycle. And that's exactly what we're seeing there. We're seeing that it's actually jumping all the way to the F7 address, and then it's moving through to EA, EC, EE, then on to 0, and then the 0 has been output, then it's going to F4, EC, so it's jumping through. So you can see there's where the address is about 0, it's going to F4, F0, F2, 0, and F4, EC. So it is looping round, and it's jumped from this start address of FF0, FF2, and then it's gone to this FFF7EA, then onto EC, EE, then onto F0, F2, putting the 0, F4, and then jumping back to EC again, going through all the way at 0, then jumping back to EC again, then going through, then jumping back to EC again. So that's all working. Now I'm going to connect the LCD display. It's a 1602 display that I got from eBay for about £3 or so. It has 16 pins. And we can see here that it has 8 data pins. So I'll connect the D0 to D7 output of the 86 to those 8 pins. But first I need to connect the first 2 pins to power. So before we do that, let's connect it into this board. I'm going to put it in, say, there. Move these power lines out of the way so we can get it in flat. Make sure all the pins are in place. There we go. So VSS is ground, so we connect that to ground. Next is VDD, which is +5. So I'll connect that to +5. Next is contrast. So I'm going to use a variable resistor here. You connect a resistor to ground and that controls the current to control the brightness. So I'm using this 10K variable resistor and I'm going to just connect the middle pin to pin 3 on here. So if I connect that in there. Like that, and then I can connect pin 3 to the middle pin, and then the other pin to other pin on it to ground. Next is RS, RW and E, which are signal pins, and then the data lines, and then finally we have A and K. A is the anode, so it goes to 5 volts. So connect A. To 5 volts. And K is the cathode, so connect that to ground. The 8 data will connect to the D0 to D7 data bus pins. What we're looking for is an enable pin, much like the enable pin on the EPROMs, as in exactly the same fashion as we did for the EPROM. We want to set the address for this LCD device. The EPROM we set to be in the range 8000 to FFFF, and so when the 8086 is talking it across the bus, the only device that responds is the EPROM. And so I want to set an address, i.e. a memory map, so that the LCD displays responds to a specific address range. And in this case, I'm going to be setting the LCD display to be 6000. So when the address is 6000, the LCD responds. And in the next video, we'll look at how to enable the LCD on the memory map at location 60000. Although the LCD although it has an E signal, it's not an enable like on the EPROM. So we'll explore that too, and join me in the next video.